Hello, back for part 2 of refraction. Last time we'd done a problem with refraction involving light going from air into a fiber optic cable, from something less optically dense into more optically dense. Now I want to talk about what happens when we go the other way, so from more dense into less dense. Let's say we've got air and we've got water, so now I'm going this way. Instead of from less to more dense to less dense. So I'm going to have a light ray coming in like this from the water, and it's going into the air. Here's my normal, again, perpendicular to the surface. Here's my angle right there. That would be the angle I would use. And the light that leaves the water is bent towards the normal. I'm sorry, I just said that wrong. Away from the normal. Which means that instead of coming in like that, it's going to be going out like that. So there's a couple of rays we can draw. If we have something coming in at a very small angle, well, it's not going to bend too much, so it might bend out like that. We can go a little bit higher, and let's go in between here. So that will come out like this. And at some point, if you see what's happening, as we go this way, as the angle in water gets bigger, the angle in air is also getting bigger. But there's a limit to how big it can get. At some point, we're going to hit an angle in water where it bends so much it comes out at 90 degrees. That is a very special angle called the critical angle. So the critical angle is when the light that comes out is coming out right at 90 degrees. So we'd have the angle of incidence, the incoming angle there, and we'd have the angle of refraction at 90 degrees. So when we have this at 90, this one is defined as the critical angle. So it's a special point. We can figure out what the critical angle is, knowing what our two materials are. So let's say we're going from water into air. Okay, so there's going to be a range of angles at which the light ray in water will go whoop, into the air and bend away from the normal. Let's find out what angle it is where it bends so much that it's right at 90 degrees. So we're going to go from water into air, and this only works if we're going into something less dense, because moving into a less dense material means we bend away from the normal. So our Snell's law equation for water into air, N water sine theta water, equals N air sine theta air. All right, index of refraction of water is 1.33, and the water, that's the incoming angle. This is our critical angle. That's what we want to solve for, because that's this one right here. Equals index of refraction of air, 1.0, times the sine of what? Okay, well, if we have the critical angle coming in, then the outgoing angle is 90 degrees. That's the definition of a critical angle. So if this is critical angle, this has to be 90. That's how we define the critical angle. All right, let's look at this. Well, there's only one unknown. Sure. And if you look at this side, if you remember what the sine of 90 is, or type it in your calculator real quick, hey, it's 1. So this whole side becomes 1.0. All right. I want to solve for the sine of the critical angle, so it's going to be 1.0. Let's bring that 1.33 to the other side. And again, to get the angle, I need to do the inverse sine. So the critical angle is going to be the inverse sine of 1.0 over 1.33. And if you do the math for water, it's around, oh shoot, I think it's 48 or 49. Can't remember right now. So the critical angle is 49 degrees. Now that's only one critical angle. That's for one combination of materials. That is only going to be the critical angle for water to air. If we were to try to do this for glass to air, well, that would have to change. The index of refraction of glass is different, so this number underneath would be different. We'd have a different critical angle. So every combination of two materials has a different critical angle. And so it's not something you can memorize. All you can memorize if you want to try memorizing is that if it's critical angle here, 90 degrees here, because that's the definition. Other than that, nope, it's going to be different for every combination. We could go from glass into water. This would be glass around 1.5. This would be water at 1.33. So it would be 1.33 over 1.5, different angle. So just keep in mind that critical angle is different for every combination of two materials. All right, let's now use this in a problem. In the previous video, I had a light ray going from air into a fiber optic cable. So we had a cable and we had light ray hitting the end of the cable and entering into the cable. My normal was like this, and then it bent, because we're going into more dense material, it bent towards the normal and came out like that. Now I want to go the other end of the cable. So we're leaving the cable. All right, so we've got the other end of the cable. We still have the same type of normal because my surface is like this. So if this is the, here, let's do this. If this is the fiber optic cable, the light's bouncing around inside and trying to leave on this surface. So if this is the surface, this is the perpendicular, the normal. All right, we're going to have light that's trying to leave, and it's going to come in at some angle to the normal, so the angle in the fiber optic, and we want to see what happens when it hits the air. All right, so the first one I want to do is an angle in the fiber optic of 30 degrees. So the angle in the fiber optic cable is 30 degrees. What's the angle in air going to be? All right, well, it's going from more dense to less dense. It bends away from the normal. So instead of coming like this, it's going to be steeper down. I would expect the angle in air to be bigger than 30 because it should bend away from the normal. So let's see if it is. Our Snell's law equation then. So we're going from fiber optic into air. Index of refraction, fiber optic, sine of the angle in the fiber equals index of air, sine, angle, air. I want to know what this is. I know the index of refraction of air. I know this from the problem, and I'm given this in the problem. Great. So 1.44 sine of 30 degrees equals 1.0 times the sine of the angle in air. Get rid of that, doesn't matter. And if you solve this one out, you get an angle in air of 46 degrees. All right, I was correct. Woohoo! I know what I'm doing. So it's bigger than 30 because when we go into a less dense material, it bends away from the normal. So if this one was 46, the angle in air was 46. All right, now how about if the angle of incidence, the angle in the fiber optic, is 50 degrees? Okay, well, it's going to be pretty much the same equation, right? So 1.44 times the sine of 50 degrees equals 1.0 times the sine of the angle in air. All right, if we do this part right here, again, that doesn't matter, you get 1.103 equals the sine of the angle in air. And that's where your brain should say, wait a minute. The sine of any angle has to be between 0 and 1. Because the sine, so if we've got our angles here, so if we have some line like that, the sine is the vertical part of that triangle there. The sine is the vertical. And it ranges from 0, if you're here, to +1, to 0, to -1. So if we try to take the inverse sine of that, your calculator is going to be very unhappy. It will give you an error message because it will say, I can't take the sine of that because it's undefined. There is no sine, there is no angle, I should say. There is no angle where the sine would be bigger than 1. This is your cue to say, oh, this is total internal reflection. This is TIR. Okay, and what is TIR? Total internal reflection. So what happens is we are bigger, 50 degrees here, is bigger than this critical angle. And so what we have is an angle bigger than the critical angle, comes in, and there's no way it can bend more than 90 degrees. So what happens is it bounces right out at the same angle it came in at. Behaves just like a mirror. So if we're greater than the critical angle, it just bounces right on out. And it's called total internal reflection. Reflection because it's a bounce just like a mirror. Total internal, all of the light gets bounced off inside. So all of it inside reflected. So that's TIR. And whenever you have an angle greater than your critical angle, then this is what's going to happen. It never leaves. So this light, if it comes in at 30 degrees, it will go out at 46. If it comes in at 50 degrees, it's not going to leave. What's going to happen is it's going to come in at a steeper angle and it's going to bounce right back out. And this is the cool thing about fiber optics, is you can just have it keep bouncing, bouncing, and bouncing. That's how the fiber optics works. We'll see a demonstration of that in class. So total internal reflection happens whenever you're bigger than the critical angle and you're trying to take the sign, the inverse sign of something that's bigger than 1. So mathematically, this is what you see when we have total internal reflection. And conceptually, this angle, 50 degrees, must be bigger than the critical angle. A good practice problem for you to do right now is figure out what the critical angle is from fiber optics into air. I know it's between 30 and 50. I don't have it in my head right now. So find out what is the critical angle going from this fiber optic at 1.44 into air. And then it should be between 30 and 50. So anything bigger than that critical angle, total internal reflection. It all bounces off inside, never leaves. So that's total internal reflection. That's the second part of refraction. And there's some fun demos we'll have, but for problem solving, it's going to be your job to know when total internal reflection happens. Only ever happens going from more dense to less dense, and it only ever happens when the angle, the starting angle, is bigger than the critical angle. So that's it in a nutshell. All right, good job.